If you're working with a foam that needs to feel silky, smooth or creamy, either in your mouth or on your skin, then this could be for you. Silky, smooth and creamy foams have the ability to both maintain separation of surfaces and also allow those surfaces to slide over each other. Separation of your tongue and your palate in the presence of, for example, a creamy beer or a cafe latte is a really good example of this. So we took a Kruss Dynamic Foam Analyser and a TA Instruments Discovery Hybrid Rheometer fitted with a Rheo-Microscopy capability, and we use this to investigate how bubble size influences the cushioning and lubricating ability of a foam. Now I say we, but it was in fact our very talented Jacob Turner who did all the hard work here. We took an aquafaba egg alternative as our standard material, and we started off by creating foams under well-defined conditions. So the foam analyzer has various methods for creating the foams. We chose sparging, where you blow a gas through a filter to create the bubbles, and we also chose a high-speed whisking attachment. Sparging gave us a coarse foam of a very wide bubble size distribution, and whisking created a micro foam of very small bubbles. In fact, this histogram belies the magnitude of the differences that we're seeing. And if we switch the bubble count axis from a logarithmic to a linear scale, you can really see the huge dominance of tiny bubbles in the whisked foam. So we then took those two foams and we performed tribology measurements on a Rheometer to assess their lubricating ability. As we suspected, the smaller bubbles led to better lubrication, with the whisked foam proving significantly more lubricating than the sparged foam. So that was a relief. Our hypothesis so far has been supported by the experimental results. So smaller bubbles have a higher internal pressure. That's why it's always harder to blow up a balloon when it's smaller than when it's already partly inflated. So my hunch here is that the smaller bubbles act like a layer of ball bearings, effectively, allowing rolling lubrication between those surfaces, and crucially also for smoothness, maintaining a separation of those surfaces. So next we wanted to assess the ability of those foams to support and separate surfaces. So we thought, what if we compress the foam and we measure the supporting stress between the plates of a Rheometer as they come closer together? If the whisked foam has a preponderance of smaller bubbles, then those bubbles should be able to provide a more rigid supporting layer. At the same time, we thought it would be super cool to use TA Instruments' modular microscope accessory to be able to capture the compression of those bubbles and image that compression from underneath the plate as it's happening. So the results turned out really well. The smaller bubbles seem to be supporting the squeeze forces better than the larger ones, and I think this cushioning would also play out in the mouth between the tongue and the palate and on the skin. And the live imaging during the compression really shows the differences between the two foams. We were really pleased with this study and we want to get into this further. If you are a visionary, creative researcher and you're working with any kind of foams and you want to be able to deliver creamy and smooth for your products, then please get in touch. We would love to work with you. So a big thanks to Jacob for his work on this, and a huge thanks to TA Instruments and Kruss for producing such fantastic Rheometers and surface and interfacial analyzers. Catch up soon.